All right, now in this video, we're going to learn how to find the term symbols for atoms that have many electrons. So beyond hydrogen, moving up to the exciting atoms known as like helium or lithium, things like that, okay? So the structure of the term symbols is the same as the structure of the term symbols we use for just the hydrogen atom by itself. So it's still going to be, roughly speaking, something that looks like this. So we have the generacy as a superscript, and then the orbital angular momentum turned into a capital letter, and then the J eigenvalue, or the J value underneath, the total angular momentum quantum number, as a subscript to the right, okay? But what makes it different now when we're talking about many electron atoms is that each of these terms comes from a sum of all of the electrons in the atom. So for example, now the capital L corresponds to we're not just taking the orbital angular momentum of the single electron and then turning it into a capital letter. This is going to be a sum, but a vector sum of the orbital angular momenta of all of the electrons in the atom, right? And so it's going to be the same thing for the S. The capital S is going to correspond to overall sum, sort of a vector type sum of all of the electrons in the atom, and also the same for J. Okay, and so this is what makes it a little more complicated than it was for the hydrogen atom, and that's what we're going to talk about here. All right, so there's basically three different cases that we're going to talk about here, and it's going to depend on the configuration. So, another thing that makes the atomic term symbols more challenging for many electron systems compared to the hydrogen atom is that for the same configuration, you could have many different and quite different term symbols. And so that means that what we're going to do is we're going to start from a given configuration and then come up with a few different rules or processes to find all of the term symbols that would be compatible with that configuration. All right, so the first rule of these is the easiest to use and the simplest. And the first rule basically says that for completely occupied shells, for completely full or closed shells, they correspond to having a big L of 0 and a big S of 0. Okay, so what I mean by that is if you have a shell like 1s2, this is completely full because you can only have two electrons. You can have a spin up and a spin down that both have the 1s orbital. And so this is completely full, and so a configuration like this will always correspond to an L equals 0 and S equals 0. And because of the rules for everything else that follow, that means that this would also correspond to a J equals 0. And so basically for everything that comes after this, in terms of how to be coupled to angular momenta of many electrons, these won't contribute anything that's interesting anyways. And so we can basically ignore completely closed shells. Right, and so this is true if you have a 1s2, but it's also true if you have 1s2, 2s2, 2p6, anything like that, anything with a completely full shell, this will still always correspond to L equals 0, S equals 0, J equals 0. Okay, so that makes it pretty easy. And so what it means is that when we're trying to find term symbols, we have to focus all of our efforts on finding or on dealing with partially filled shells. Okay, and that's where the next two cases are gonna lead us. Okay, so I'm gonna clear this, and then we're gonna talk about there's two different distinctions we have to make about what it means for a partially filled shell. So we're going to start with the easy one first, and this is going to be for inequivalent electrons. So what do I mean by inequivalent electrons? This is going to be shells that look something like, let's say, 1s1, 2s1, right? We have two electrons. They're in partially filled shells, right? It's 1s, we only have one electron in s1 and the 1s, and you have one electron in the 2s. So neither of them is fully occupied, but they are inequivalent because they are parts of different orbital spaces, right? So by contrast, if you had a configuration that was like 2p2, right? This is partially filled because there can be up to 6 and 2 is less than 6. But the electrons are in the same set of configurations, and so that means these are equivalent electrons, and so we have to deal with them separately. All right, but that'll be our case number 3. And so first we're going to start with talking about inequivalent electrons. And everything that we do here is going to be inside of what's called the Russell-Saunders coupling scheme. Okay, so this is a scheme, and really the idea behind Russell-Saunders is that the orbital angular momentum operator, so L squared, right? We know that in the presence of spin orbit, it does not commute with the overall Hamiltonian, but that deviation from commuting is small enough that it's still useful to think about the atoms in terms of the L and S quantum numbers. And so we're going to start by first chasing after L and S separately, and then we're going to see how these combine into J. And again, this may not be exactly true, right? We know that we can't exactly specify L and S in these systems, but it's a good enough representation that it's very useful, and we care more about it being useful right now. And this type of scheme will be really valuable for light atoms, and once you get into heavier atoms, then you have to take a completely different tactic to find these, which we're not going to talk about in this course. Okay, so the basic idea here is that first we're going to couple the orbital angular momenta for all of the different electrons, and then we're going to couple the spin quantum numbers for the electrons, and then we're going to use these to find every possible combination of L plus S to give J. Okay, so let's go through, let's say we'll do 2 examples. The first example, we'll sort of move over here. So let's see what happens with this 1s1, 2s1, right? So first we're going to couple the orbital angular momenta, and this is going to give us, all right, so we have L1 in this case is 0, so the 1s has L0, and L2 is 0, and so that means that big L, the only allowed values for big L, will also be 0. Right, and so what's happening here is it's the exact same rules for adding up angular momenta that we saw previously in the course. So the big L can go from the difference of the two to the sum of the two. In this case, because they're both 0, it just means you only have L equals 0. Okay, and now we also couple the spins in exactly the same way. So we have S equals 1/2 and S equals 1/2. So the spin for this electron is 1/2, the spin for this electron is 1/2. And so when we combine these, it means we can have from S equals 0 to S equals 1, right? So we can either have 1/2 minus 1/2, or we can have 1/2 plus 1/2. So that gives us S as 0 or 1. And then that means we have every possible combination of both of these sets will be the base term symbols we'll be allowed to have, right? So this is going to correspond to a singlet S and a triplet S, right? Singlet because for S equals 0, the degeneracy is 1. Triplet because for S equals 1, the degeneracy is 3. All right, and then from here, the very last step would be to couple the orbital plus the spin angular momenta to get the overall J value, which for these 2 examples is actually really simple because L is 0, and so the allowed value for J is just going to be simply S. And so here it's going to be 0, and for here it's going to be 1. Okay, so we have 2 possible term symbols. We have a singlet and a triplet for the 1s1, 2s1 configuration. Yeah, let's do one other quick example. We're going to look at what we get from a 2p1 and a 3p1 combination. Right, these are still inequivalent because they're in different orbital sets, and so we can follow the same process. So first we're going to couple L. So if we have L1 equals 1, L2 equals 1, this means that big L can either be 0 1, or 2, right? And that comes from there being, the smallest value you can have is the difference between the two, which is 0, and the biggest value you can have is the sum of the two, which is 2. Okay, and then we still have 2 spins with a couple, both of them are 1/2, and so we have the same allowed values of the spin that we had in the previous example. And this will give us s equals 0 or 1. So now we can have every possible combination of these as term symbols. And so if we go through it, that means we can have a singlet s, a triplet s, a singlet p, a triplet p, a singlet d, and a triplet d. Okay, so there are 6 sort of base term symbols. And then to figure out the final term symbols, you would couple L and S to find all of the possible allowed values of J for each of these. And I'm going to leave that as an exercise for you because it's something we've already done over and over and over again at this point. Now, the last case we're going to look at is what to do when we have equivalent electrons. And this is definitely a trickier case because there'll be lots of rules that tell us which configurations are allowed or not allowed when we have equivalent electrons. So there's 2 big rules off the top that we're going to have to always obey. So rule number 1 is the Pauli principle, right? So the Pauli principle, very briefly, says that we can't have 2 electrons that have exactly the same quantum numbers. Okay, so we can't have 2 electrons that both have, let's say, m sub l equals 1 and m sub s equals 1/2 for the same sort of configurations, right? So this is more or less how you get to the double filling rule that you normally have in Gen Chem, but it's specific about the exact same set of quantum numbers. Okay, and then rule number 2 is that electrons must be indistinguishable, right? So in other words, if you have 2 electrons sort of sitting in 2 different orbitals, so this is one configuration, up and down, and you can imagine having another configuration, which is like down and up, maybe. Well, because electrons are indistinguishable, if these are the same orbitals, then these 2 configurations are exactly the same thing, right? Because in order to tell the difference between these, you have to be able to say this electron is electron A, let's say, and it's up on the left versus down on the right. But that is that would require you being able to distinguish them, which is not allowed. And so we need to take into account the fact that these are actually indistinguishable. Okay, so the overall process is going to go in the following way. So I'm going to map it out, and then we're going to work through one example together. So first, we're going to write down every possible combination, or every possible microstate, or every possible micro configuration that we can get that would correspond to the set of electrons in this shell. I'm going to write this as every possible microstate. Okay. And then the second step is we're going to start identifying L and S manifolds from just pattern matching, basically. And I think the example will help clarify what I mean by this. But basically, we're going to look at the pattern of which allowed values of m sub L and m sub S we have, and then what we know about how angular momenta sets come, or how manifolds come. And then we're going to use those to just basically match patterns and identify what combinations of L and S are allowed. Okay, and then we keep doing this, sort of repeat until we've assigned all of the microstates that are consistent with the configuration. And then at the very end, when we're done with that, we will sort of do some sanity checks to make sure that we haven't done anything completely crazy. Okay. Okay, so if I write down every single allowed configuration, it's going to look something like this, where I'm just organizing these according to the values of m sub l and m sub s. These are slightly different. Notice this is capital M sub L, so this corresponds to summing up the m sub L for every single electron, and same with m sub s. So big M sub s corresponds to just summing up the little m sub s for every single electron. And what makes this simpler and easier than the big L and the big S is that this is just normal adding up, not factorial, just normal number addition. Okay, so the largest possible m sub L that you can get for or the example we're going to do is we're going to do 2p2. Right? So the largest possible m sub L that you can get is 2. This would be corresponds to an m sub L equals 1 for electron 1 and m sub L equals 1 for electron 2. And the absolute smallest you can get is -2. And then for m sub s, the largest you can get would be 1. This would be correspond to both electrons being in an up configuration. And the smallest you can get is -1. This would correspond to both electrons being in a spin down configuration. And so we're going to arrange all of these microstates just in a table like this, right? So the values of m sub L go -2 to 2, and the values of m sub s go -1 to 1. I'm using a little bit of a shorthand to write down these configurations. And so if you notice, I'm using things like 1 plus, right? And so what this corresponds to, what 1 plus would correspond to is this would correspond to an electron in the P1, so m sub L is equal to 1, with m sub s equals plus 1/2. Or another example, 0 minus would correspond to m sub L is equal to 0, and m sub s is equal to -1/2. But we're looking for configurations of both electrons, since we're writing out both of these, right? So these things in parentheses, this is just to say that. So for example, if we look at this term here, this is electron 1 has m sub L equals -1 and m sub s equals plus 1/2, and this, the electron 2 has m sub L equals 0 and m sub s equals plus 1/2. Okay, so these are all of the combinations that you can get for the 2p2, or in fact np2 system. I want to draw your attention to a couple things first. So notice that these corners here are empty. And the reason for this is that you cannot fill these and also satisfy the Pauli rule, right? And so in order to have something up here, you would need to have 2 electrons that both have m sub L equals -1 and m sub L equals plus 1/2. But we can't have 2 electrons with the same exact set of quantum numbers. And so that means that this is empty, this is empty, this is empty, and this is empty. And then there are some similar things that happen around here, where there are some configurations that you might have naively thought should be there, but they're not allowed because of the Pauli principle. Okay. So now what we're going to do is, again, this is basically pattern matching. So we're going to go through and we're going to start looking for patterns that match what we expect for a particular value of L and S. And so the best way to do this is to look for the largest value of m sub L first. And so here that's 2. And then look for the largest value of m sub s that has the same value of m sub L. And so this here, that will correspond to 0, where there's only one m sub s value here. And so for if the largest combination here is m sub L equals 2 and m sub s equals 0, then that corresponds to having a let me write this over here. This corresponds to having L equals 2 and S equals 0. Right, so we're just deducing that because we have something here, and we don't have anything with m sub L equals 3, and we don't have anything with m sub s equals 1 or anything like that, that means that this must belong to something that is L equals 2 and S equals 0 in structure. Okay, and so that means that we can sort of conclude that there will be at least one term that has a singlet D term symbol coming out of this. All right, and so this is sort of just like pattern matching. And now what we do is we go through and we cross out all of the configurations that would be consistent with a singlet D. So for a singlet D, we know we would have m sub s equals 0, and then m sub L goes from -2 to +2. And so we can just cross out one configuration for each of those possibilities. Okay, and an important point here is that it doesn't actually matter which configuration I'm crossing out. We're only using this for a counting exercise, right? So we write these out just to count them. We don't actually care about what the specific configurations are. And so we're not trying to use this to assign which configurations go to which term symbols. We're just trying to use it to get an overall count for the number of configurations that are here. Okay, so that's the first one. And so that means that we've now assigned one term symbol that's a singlet D. And now we keep doing the same thing. So we look for the largest m sub L that's left, and that's going to be 1. And then within m sub L equals 1, we look for the largest m sub S that still exists. And that's also going to be 1. And so if you combine these two together, that means that we should be expecting to see an L equals 1 and S equals 1 subset, which corresponds to a triplet P. Okay, and then next we know that for a triplet P, there should be m sub L equals -1, 0, and 1, and m sub S equals -1, 0, and 1. And so that's 9 different configurations, and we're just going to cross out one configuration for each of these combinations. So we're going to go through and we kill that one. All right, we just do 1 across the board. Okay, and we've killed 9 different configurations that corresponds to the triplet P now. And finally, we look at what's left. There's one term that's left, and it has an m sub L equals 0, and the maximum m sub S is also 0. And so this must correspond at the very end to L equals 0 and S equals 0, or in other words, a singlet S. And we can finally cross that out. Okay, so now, and with that, we've found all of the possible term symbols, except that we would then go through and recouple these with the L plus S in order to get the final J values. Okay, but we can kind of see this as quite a bit different in structure than how we found the term symbols for inequivalent atoms. All right, and so now the last thing you want to do when you do this is you just want to do a quick sanity check to make sure that you have the same number of states here as you did down here. Okay, so we just counted all of the distinct states that we got down here. We would get 15, and that corresponds to the number of configurations here should be 6 choose 2. Sorry, 6 choose 2. Okay, so this is a probabilistic thing, and what it corresponds to is what it's equal to is 6 factorial divided by 2 factorial divided by 6 minus 2 factorial, and this is 15. So we should end up with 15 configurations just based on the indistinguishability and the number of different ways that you can arrange these electrons, and that's exactly what we get if we count up all of these. Now if we count up the configuration based on the term symbols, for a singlet D, we should have 5 configurations. For a triplet P, we should have 9 configurations, right? We have 3 spin times 3 orbital angular momentum configurations. And for a singlet S, we should have just 1. So add all those up, and you also get 15, right? So that's kind of a nice sanity check at the very end.